Okay, so thank you very much. Thank you. Let's thank Axel and Raphael for inviting me. I've had a very enjoyable month here, and I've learnt a lot. I should explain that I'm a mathematician by background and training, so I know little physics and very little chemistry. I've done some work in similar subjects before, so I'm going to talk about this afterwards, but since Mayo talked about it and it follows on from the end of his talk, I'll talk about this first. This is the work from Louise's group on forming polymers. These are copolymers. They've got sequences of lefts and rights, so you can form things like D7, D6L, D5, D2, and if everything followed the Gaussian distribution, you get these white bars. That's Pascal's triangle, binomial theorem that Mayer had in his talk. But what he actually observed are the grey bars. So you see a massive overexpression of these, which we'll call homopolymers. This is the pure L7 and the pure D7. The ones in the middle are called heteropolymers. These are mixtures of lefts and rights, and these are, the central ones in particular, are very underexpressed from what you'd expect from normal distribution. And he managed to get up to length 10. And even in these you see that it's not a Gaussian distribution. One of the things they mentioned at the end of one of their papers was that this requires a high-order Markov process. So a Markov process is a system where the next state depends only on the previous state, and it doesn't have any further history. It doesn't remember any further back in time. So what that would mean for a polymer is that the distribution for polymers of length 7 would only depend on the distribution of polymers of length 6, and not on the previous one. So we say that a polymer so this is similar results for chains of length 3, 4, 5 and 6. And okay, so those are I'll come back to those in a minute. So a first order Markov process, which is all that we actually need to model these results. That's what I explained. So this is written down by Flory. It's very natural. It says that you have a polymer here, and it's got some sequence of lefts and rights. I'll use A and B instead of left and right, or R and S, or D and L, or anything. A and B are just two types of polymer. So X's could be anything. It could be either A or B. It doesn't matter what these are. What matters is the last one on the chain and what you're adding to it. So we have a polymer that ends in A, adds to another monomer that is A, and gives you another polymer that's the same as this one, that's got two A's on the end, and that's going to happen with this rate coefficient KAA. Polymer that ends in B could have B added to it, and that happens at some rate KAB, and similarly for polymers that end in B and added to A and B ending in B. A higher order Markov process would be much more complicated, because you'd have polymers that would end AA, you'd have another set of polymers that end in BA, and these second order Markov process would remember the stage before as well. So these two reactions would happen with different rates. So that would be quite a much more complicated system. And actually I don't think we need that sort of process in order to model our results. So if we go back, I'll spoil the fun and show you the fits that we've managed to get. So here we've plotted the black bars on the left and on the right of the experimental results from Louise's group. The first white bar here is what you'd expect from a Gaussian distribution, from the normal distribution of the binomial theorem, and these two white ones are two different sorts of fit. One is the best possible fit, which is this one, and the other one assumes symmetry, where A's and B's are treated the same. AA is treated the same as BB, but AB is different to BA. And so this is the fit that we can get for polymers of length 6. So I think these are reasonable results. And those are for polymers of length 10. You see it's very, very different to what you'd expect from this Gaussian distribution, but what you'd expect from our first order Markov process is a reasonable fit. Okay, so what we do to actually work out what the distribution should be is write down a set of chemical reactions. Looking back on this as I was writing this, it seems this reaction scheme seems very complicated for what we actually end up predicting, but I think that's just the way I do things. So well, I'll say some more about that later, perhaps. So I'm going to write down these things called CRS-A and CRS-B. These are, C is just a generic letter. These are polymers of the C's with a superscript A are polymers that end in an A, and C's with superscript B are polymers that end in a B. Clearly, because we're having this first order Markov process, we need to know how many polymers there are that end in A and how many polymers there are that end in B. That's a crucial thing because the rates of addition are different, and we're going to have different things they add on. But it's also useful to keep track of how many, because what we want to produce at the end of the day are these graphs of D2L8 and things. We want to know how many, given a chain, how many L's and how many R's, how many A's and how many B's are in the chain. So this is what the R and S are. This R means there are RA's in it and S and SB's in it. So this is a chain of length R plus S that's got RA's, SB's. Most of those elements, it doesn't matter where they are. All we need to know is what the last one is, whether that's A or B. So that's what this CRS-A and CRS-B are. And they're going to undergo these chemical reactions. And if we write down a set of mathematical ordinary differential equations for the rate of change, so these are dots on, which means the rate of change in time for each possible quantity, then we end up with all these different reactions. I won't go through all the gory details, but this is complicated because we're trying to think about this in a two-dimensional space. This isn't physical space, this is a composition space with R's and S's. So things along here are polymers, things like C50A, so that's a homopolymer with 5 A's in it. Things up here are things like C04S, it's a tetramer of 4 S's, but in the middle we've got things like C54, which is a polymer of length 9, and there are 2 of those because there's one that ends in an A and one that ends in a B. And you have to worry about all the different possible combinations, and it's pretty gory when you write down all of these. But fortunately there's some mathematical techniques where you can simplify all this, and I won't go through all the details, but I think it is useful to write down a detailed microscopic model of what's happening at the fundamental level. So those microscopic models you can't actually fit to experiments because then, I don't think Mayer could tell me what the concentration of C2317 is at a particular time. But what we can measure are things like the total amount of polymers, the total number of polymers. We might be able to measure bulk concentrations. And so from a microscopic model it's useful to then be able to extract macroscopic information that you might measure in an experiment. So these are macroscopic quantities, the total densities, the total mass of stuff that ends in an A, or this is the total mass of A stuff, the total concentration of A monomers, whatever form it's formed in, the total concentration of B polymers, whatever form it is in. And from
those are the ones that end in A, or the number of units that include
the total number of A that you've got in your system.
Okay.
Yeah, you can also write down ones that end in A as well. So you can have the amount of A in polymers that end in an A, and the total number of polymers, and you can form differential equations for these macroscopic quantities. And those don't really depend on other macroscopic quantities, so you can end up with a much simpler system of differential equations which you can solve. So although you might not be able to solve a previous horrible system, by just working with that system you can write down a simplified system that you can analyse. So that's the solution of those differential equations, and in this particular system you can work out the average polymer length, and that grows with time. So some of the things that you can get just trying to explore this model in a bit more detail, not just to compare with Luigi's results. This is a random system, that's where all the rate coefficients are the same. You get these distributions which are quite broad, and if you've got equal numbers of A and B polymers, you get normal distributions. So, a heteropolymer dominated system. So this is where we assume that, so you've got these four quantities for KAA, KAB, KBA, KBB. So this is a system where these two dominate, so you say that these two only happen very slowly, so you very rarely form homopolymers because their rates of addition are very small, and that's some reason why these dominate, and so you'd expect to get AB chains. So then you get a similar sort of normal distribution, but this is very tightly peaked around R equals S. And the more interesting one is the reverse case, where you tend not to get AB polymers, but you do get lots where the rate of forming homopolymers is very high, KAA and KBB dominate KBA and KAB. Then you tend to get homopolymers, but only at the shorter lengths, because if you still have these KBA and KAB non-zero, you still eventually, after a certain number of A's, you get a long sequence of A's and B's, but eventually you probably get one of the opposite ones formed. So you get these very broad distributions. So these distributions have two sorts of features. At short lengths you get homopolymers, but later on polymers get so long that you tend to do get crossovers. And if you go back to the detailed model with CRS's A and B, you can define things like the Shannon information entropy for the system and run lengths and other things that might be measured. So that was just a brief summary of some work I did with Peter Coveney based on work that Luigi's group has done. Incidentally, I think for Mayer, I think this assumes that the polymers only interact with the monomers, whereas I think your later results where you get longer chains, you have to worry about polymer-polymer interactions.
Yeah,
so it's
I
a
think
bit more complicated.
I think that the first part, as we know this, that in the first stages of the polymerization, when you're dealing with isolated molecules, I think your model of Markov mechanism is correct. Because what we call this asymmetric induction, because if you analyze, even under our conditions, the dimer is 1 to 1 to 1.
Yeah.
It's not 1 to 2 to 1. It's not like the long one.
Yeah.
Then if you go to the tetramers, they precipitate.
Yeah.
They separate, and we can detect actually the cluster, the colloidal particles which are formed.
Yeah.
What we don't understand, how this colloidal particle can continue to grow, because they are probably hydrated, they are strongly hydrated, and therefore they have different properties that compare into the solid, because if you take the solid out and put it inside, it doesn't work. Only these clusters which are formed, and once they are formed, actually they induce very high stereospecificity.
Yeah.
So your your model is actually the first part of the experiment, and because we use amino acid as initiators, where the percentage of this initiator is very, very low, and the reaction competes with hydrolysis, you cannot do that.
So we probably need to go back to here and add in other effects, but we should talk about that later.
What is also interesting that Luigi also did it also with tryptophan, right? And we found that tryptophan cannot form the beta sheet. And therefore the behavior of the tryptophan is very similar to what Luigi found actually after decamers in tryptophan, but they don't form the beta sheet. And therefore it's another demonstration that you need a beta sheet for the formation of the longer peptides.
Okay, so what I'd like to talk about as well is models of chiral crystallization. So this is something I've been doing over the last month. This is very much work in progress, so it's going to end rather abruptly, and I don't really have any definite conclusions yet, but I'd like to just show some of the results we've got. So we've heard lots about the Frank model, where we get symmetry breaking. So this is an open system, so it requires the input of material. It has mass build-up, it has cross-inhibition, enantiomeric cross-inhibition, which takes out equal numbers of left and right. And that sort of amplifies random stochastic differences. So that's one of the mechanisms which gives you the symmetry breaking. So my classic pitchfork pipe. And this soy model, which accelerates and amplifies EE. Sato's model, and I'm going to say is very similar to what Sato's had to say. So the fundamental system that he was looked at was this, which has some sort of feedback. It has autocatalysis built into it. Samsa's model, which again has this cross inhibition, which takes out, which is a competition effect between lefts and rights, and takes out one, and so accentuates symmetry breaking. And analyse that.
I mean, I think that's the wrong Saito model. That was for polymerization, right? What you meant actually is maybe the other model for crystallization, which looked not like this. That's not the model that you presented yesterday.
That is the model for the soy.
Okay. Well,
yeah, right. Oh, sorry. Yeah, yeah, not for crystallization. Yes. Okay.
Looking at models that exhibit symmetry breaking.
Then it's okay. Yeah.
Yeah, there are. I could give lots of things.
Yes.
So what we set out to do. So this was suggested by Axel and Raphael, and I've got some input from them on this. This to try and look at a model of crystallization. This, for example, this work of Viedma and grinding up crystals that sends a system to homochirality. And thinking about crystallization when you've got grinding, we didn't see any reason for cross-inhibition to occur in such a system. So one of the aims was to write down a model that had symmetry breaking without cross-inhibition. To see if competition alone is enough to get symmetry breaking. And then also to construct some sort of maximally simplified model of such a process, just to see if we can understand what the fundamental mechanisms are. So this is a summary of where we start from. So what I'm going to assume is that we've got two sorts of crystal. We've got crystals across the top, which are type X, and crystals across the bottom, which are type Y. And these grow by addition. So you've got particles of size 4 that can grow to size 5 or 6 by some addition of monomer. And these can fragment rate B, giving rise to monomer. And the same for these crystals, type X. I'm also going to assume that we've got this third sort of cluster, which are in the middle. These are these Cs, and these are amorphous crystals. So I'm going to assume that at small cluster sizes, things tend to be amorphous. Small crystal nuclei tend not to have any particular crystal structure. So if you really think of some sort of phi being some sort of how when you left or right, at small cluster sizes you've got some potential energy predicting like that. When you get very large, they do adopt a crystalline structure. So at very large, you have some sort of free energy which is symmetric and has either usually left or right. And somewhere in the middle, there are sort of medium-sized crystals which could be medium-sized crystals which have some sort of potential energy with three wells. It could either be right, left, or it could be amorphous. And in the middle, in this region, there could be some sort of transition rates between, which indicate how frequently, how likely you are to jump across this barrier. So you can make that transition.
You're showing that the L goes to the R through the amorphous space?
So we don't let L go to R.
To the amorphous space?
L can go to the amorphous space, and the amorphous space can go to the right, and it could happen both ways.
And this is the sodium chloride experiment? This is the system of sodium chloride?
Yeah, it's
Why
it's a
L cannot
mathematical
go to
model.
R directly?
Pardon?
Why L cannot go directly to R?
Well, I thought if there was an amorphous space, that's what it would go in between.
Yeah.
It is a competition about the information. You said without competition, that is a limited enantiomer selectivity, that is not cross inhibition, but that is a limited enantiomer selectivity. Information of
It's just that when things are very small, when they're very small, they don't have an enduring chirality.
Small
but
things are,
without limited enantiomer selectivity, it's not possible the symmetry breaking.
Well, as
small clusters.
depends on what
You can renounce to the cross inhibition, but not to limited enantiomer selectivity.
So small clusters aren't in any fixed shape, they're continually vibrating. If you've got
Yes,
a small
of course.
cluster of size 5,
Of course, it can be
it's a
very
random
small.
cage and it's just vibrating all over the place like a liquid droplet.
Yes, but without this amorphous, can you go to symmetry breaking?
as they get bigger, they adopt chirality, yes?
Yes.
So at that point, you could begin to do your thing.
Yeah. You'd like me to get rid of this amorphous phase?
Yeah, but if the cluster touches cluster,
Well, what I'm going to do is gradually eliminate things from this very complicated model to see what the simplest model is.
Of course, but when you eliminate too many things, then there is no symmetry breaking.
So he
Well,
wants
I'm
to keep
going
the
to, I'm
symmetry
going to look
breaking.
at some systems that have symmetry breaking and some that don't.
But there is the amorphous phase.
Well, I want to investigate models and see if that's important or not.
But an ion pair of sodium chlorate is not likely to be very chiral for a
I
long
don't
time.
speak about sodium chloride.
He is.
So we have growth. So this hopping across energy barriers are these last few terms, and I put these in to keep Mayer happy. He wanted every possible combination of things. I originally wrote this down in this model with just cluster monomer interactions, and Mayer wanted, in order to get across a nucleation barrier that clusters of size 5 and 4 could coagulate. So we've got all possible combinations of things aggregating together to give different sizes. And the ones that we're going to keep, and the most important, are dimer interactions, where things can grow and shrink by adding on a dimer, and the dimers could be crystallized or amorphous. So, if we get rid of all of this stuff in the middle, I'm just going to assume that the only amorphous thing is a dimer. Get rid of all of the others, just have amorphous dimers and monomers, and then we've got crystals of type X and crystals of type Y that grow. So we end up with this horrible systems equations. That's not to be solved, but except numerically. So we do some sort of explorations and we do simulations. So what we see is, starting from a small perturbation, we can get a symmetry broken state. So this is one type of cluster has grown, and the other type of cluster has shrunk. And that's against logarithmic time. And if we look at the chiralities, or the enantiomeric excesses, these evolve over time like this. So we have a number weighted one and a mass weighted one. If we plot the log against time, we get this region of linear growth, which is a straight line on the log graph, which means we've got exponential growth of the EE. And this is what the cluster size distributions look like with exponentially decaying. So we stripped out all the general mechanisms before. We're now going to strip out the monomers as well and just have dimers of amorphous type X and type Y, and these can grow. So clusters either grow by adding on the amorphous dimer or a dimer of the same chirality. They can't add on a dimer of the opposite chirality. We don't have any cross inhibition in the model, and this can happen. So this can grow to the next size up either by colliding with one of these or one of these, and it can fragment, or due to grinding, down to one of these, and when it fragments it throws off the next two. It throws off a dimer of the same chirality as itself. So that's the grinding. So we've got these mechanisms. Beta is the grinding, alpha is the rate at which it adds on an amorphous dimer, and psi is the rate at which it adds on a chiral dimer of the same chirality. And those are the only mechanisms we've now got in our model.
Could you say something about how important it is that it be a dimer rather than a hexamer or a decamer or something like that? Does that just sort of scale the whole thing?
Yeah, I think it just scales the whole thing.
Yeah,
if we could have hexamers, and then you'd have Y6, Y12, Y18,
sure.
and you just have 30. It doesn't matter. It's just that,
So it's the idea of whatever the smallest chiral unit is that,
Yeah.
that transfers.
Yeah. And the big assumption in this is that grinding produces a cluster, the crystal just loses a little bit,
Adjacent, yeah.
and the fragment that comes off is minute. So it's not a symmetric
Yeah.
crushing, it is something that just releases a very small fragment.
Anything that you can extract from these studies, what is the physical side of the cluster?
Well, currently I've just looked at these rate dependence, these rates are size independent.
Yeah.
So I think to do that you'd have to build in some size dependence into those, and it would get more complicated. But if you had, so often as a mathematician I try and write down mathematical models for what's happening, and so writing down a model is relatively easy. It's finding the parameters that's difficult. So if you give me a set of parameters, I'll happily do it. But finding a set of parameters is often the trickiest part.
Perhaps I don't understand well, but the amorphous, when you speak about amorphous, it is precrystallization, or it is chiral, or can be...
No, it's achiral.
It's achiral.
Yeah.
Well, that is what I was thinking. That is the limited inhibition step. It is not cross inhibition, but that is the inhibition step that allows the symmetry. This is the limited and anti-selective inhibition.
It's not necessarily the rate limiting step.
But that is a chiral.
And I would not.
Limited and anti-selective. It's the paper of Abetisov in Benas for 15 years. You can have cross inhibition or limited and anti-selectivity. I suppose Sanders can say also the same thing. Of course, this you can take the Prague model or this one, but this one should also work for symmetry. But you are imagining that the cluster is not chiral. And that is the competition step that allows the symmetry.
At the moment it goes back to a very much more simple model. So there's really only right and left, and the only way that you can go to amorphous is by having a crystal which goes all the way back to X2 or Y2, and only then it can go out to
In any
amorphous.
case,
That is certainly by no normal means what one would call cross inhibition.
There's no interaction here. If you cross out all the x's, there's no these don't these y's never interact with the x's.
But this manifold or the other manifold can lose the chirality from the amorphous.
They need to interact somehow.
Yes.
Yes. Otherwise, there'd be two completely separate systems that you could put in separate boxes.
The formation of the amorphous phase, a kind of phase, that is destroys the chirality. Yes or no?
So the
formation of the amorphous phase.
No, it's the competition for the amorphous phase. Both of these things can grow by absorbing the amorphous monomer, and it's that competition. It's competition, it's not inhibition. I think they're very different things.
The competition step is the formation of the amorphous phase.
No, the amorphous phase is there to start off with.
Anytime you make a step along the top or along the bottom, you consume or generate a dimer.
Yeah.
which is able either to go to the achiral form or to go back into elongating a chain.
Yeah.
And that competition between becoming achiral
Yeah.
and elongating a chain
Yeah.
is the thing where the competition occurs.
Yeah. But I think it's wrong to call that inhibition. It is
Yeah,
competition.
it's a competition,
It's
I
a
would
competition
say.
effect.
this limited enantioselectivity selectivity.
Yeah, and it's going to
Can
give
you
rise
say
to
about this?
an SCLX.
But you need this step to have the symmetry.
You need something to give you symmetry
Yeah.
rating. Yes. And if
We agree that.
So this is the model that we end up with, and this is the simplest model so far that will give us a symmetry breaking. So one of the features of choosing all the rates to be size independent is that you can almost simplify this. So we have the dimers, we have amorphous type X and type Y, and the other thing that we're going to think about is the total number of clusters, total number of crystals of type X and type Y. And this only depends on the number of clusters of type X and Y and the dimers. The one thing that throws a slight spanner in the works, the great problem, is that the equations for the dimers involve the tetramers, these X4s. And so really, in order to complete the system, we need to keep all the equations for the X4, and they depend on X6, and the equations for X6 depend on X8. So we can't really quite simplify that any further. Okay, so this is the simpler system. So this is without, this is only dimer interactions. This doesn't have any monomers in it anymore, and we get very similar results to what we had before. That's the symmetry breaking one. We still get exponential growth of the E. Get this slight, quite interesting effect where we put in a slight initial perturbation in order to see symmetry breaking, and even though we put in a slight success, it decays almost down to nothing and then grows again a lot later on. The one thing now is that we don't end up with particles of size 3, 5, 7, so we end up with this very spiky size distribution, but we can live with that. And so I showed that last picture. Last one was a symmetry breaking to something that's sort of 80%. This is a symmetry breaking, different set of parameters where we get symmetry breaking to something that's as close to 100% one chirality as you can see. And these seem to be very similar to the pictures that we get in the experiments. This curve a bit accelerates. So we seem to get quite encouraging results for those. And this chiral, this sort of complete bifurcation to one where you get pure homochirality, this is the size distribution for the one that's lost. It decays very quickly, you've just got a few dimers and hardly any tetramers. The size distribution for the one that's won decays very slowly, so you're getting very, very large numbers, clusters, and almost flat. So you're getting a sort of equal distribution, a very broad spread distribution of sizes. So we'd like to simplify this further, because that's still quite a lot of equations to analyse. So a natural thing to do is just to think about the system with dimers and tetramers, particles of size 2 and size 4. And so you can write down a set of equations just for that, and that's quite simple. That's just 5 differential equations to analyse. And so we could do some simulations of that. And we get these. So this looks nice. So this is a log sine. You can run it for 10, and it looks like it's reached steady state. You run it for 100, and it still looks like it's reached steady state. But you run it for 1,000 or 10,000, and eventually it becomes racemic. So this is 2 or 3 orders of magnitude that it stays symmetry broken, but it's not really at steady state. It's going to become racemic. So it looks like we're really close, and you can try changing the parameter values and looking again, and it does the same thing over and over again. The enantiomeric excesses, we put in a small initial perturbation. That small perturbation grows, and it looks like it's reached steady state, but if you wait long enough it goes back to racemic, which is not very nice. These are sort of phase planes. I don't know if these are useful, but this is the number of clusters and the mass of clusters. It very quickly reaches some point. This is where there's virtually no stuff left, no monomers or dimers left to react with, and so very quickly you get to this state, and then you evolve very, very slowly towards this racemic state. So try to understand why doesn't this quite work? What can we do anything about it to correct it? So that's the system of equations. I'm not actually going to try and solve these, but one way of analysing them just to see what happens is, instead of thinking about the concentrations of left and right, think about the total. To write the concentrations as an average concentration Z, and then theta is an n-antinomic excess. So one of the concentrations is this term 1 plus theta, the other is 1 minus theta. So when you add these two together, you just get Z, and you take the difference, you get Z times theta. So theta is x2 minus y2, x2 plus y2. And this is a much simpler, it's a nicer way of thinking about the equations, because you can see what's almost happening is this system is separating into one system here for the concentrations. This has got C's and Z's in it and W's, which are the corresponding ones for the tetramers. And it only mentions theta in a couple of places. It's not really very dependent on the theta or phi, the n-antinomic excesses. And then there's a separate set of two equations which you need, where you really need to worry about the W's and Z's as well. So this enables you to solve, instead of trying to solve 5 equations at once, you can just worry about 3, and then once you've analysed those, you can worry about the other 2. It's just a more convenient way of thinking about it. It's the theta and the phi equations you need to worry about if you want to know, can you get a chiral solution, and is it stable or not? And the condition for stability is comes down to the eigenvalues of the system. For stability, you just work out basically the determinant of this system, which is this term at the bottom, and you need the determinant to be negative in order to give you instability. And since we're dealing with concentrations, we know all of these terms are positive, and we've got a plus here, plus here, plus here, plus here. This is our only hope of having an instability. Only hope is that this term would be bigger than all of those 4 put together. So what happens in the system is that this is actually satisfied, can be satisfied at early times, can be satisfied for a time. But if you look for equilibrium, if you assume W and Z reach equilibrium, plug in their equilibrium values, this can never be satisfied. So it's impossible, whatever set of parameters you choose, for this system to have a chiral solution, and it's not racemic. You can even get these sort of transient instabilities where you put in some initial condition, it looks like it's going to stability, and then it changes its mind, and it becomes achiral again, and then it finally goes to racemic state at the end. So we return to this more complicated system, and the reason that, and try and think about what we can do to simplify it a bit further to get a system that's as simple as possible and still exhibits symmetry breaking. So I think that the problem is with the previous model is that it doesn't contain enough information about the size distribution of the clusters of each type. So we need to keep more of information in this. Before we just had tetramers, we did dimers and tetramers. We actually need to keep more information about the number, because if we keep stuff about the number of clusters of each type, we've got a better measure of the distribution of whether it's spread out. So this is satisfies the as we've got. So this is an equation for clusters of size k. It depends on k minus 2, k and k plus 2. The clusters of size k plus 2 can fragment at this rate beta, so these are size k, and they aggregate at a rate that depends on the dimers of type X and the amorphous dimers. So if you assume that this is close to steady state, you could solve this to find out something about the size distribution, and you find that the size distribution decays exponentially. So what I suggest is that we use this information, and this is quite good, gives us quite a wide range of distributions, because if you choose x to be large and this to be close to 1, you can get a distribution that decays very slowly and gives you a broad spread of sizes. If you choose x to be large, this could be quite small, because beta's large, and it could give you a distribution that gives you a lot of dimers but very few of anything else. Or x could be small, and this term could be quite large, which would give you something which had a few dimers but a wide spread. And the final one is if you choose this to be small and this to be small, you get something which almost nothing. So there's enough freedom in this sort of distribution to give you quite a wide range of behaviours. And once you've made this assumption, you can work out the number of clusters. And then you can plug that back into the equations and work out what the mass of the system is and do some more analysis, which is what I'm in the middle of at the moment. And hopefully that will give us a simpler system, which will give us simple expressions for when you get symmetry breaking and when you don't, and what it depends on, what parameters it depends on. So that's about as far as I've got. So we've got a new model for symmetry breaking through a direct competition for amorphous material. And we get this conversion between the chiralities at the small end of the distribution, which is the converse of Raphael's APED model, which has monomers, and then you get conversion between chiralities at the end of polymers. We've got a closed mass system. Mass is conserved. We don't have any input or output of the material. It's all what's in there at the start is what's in there at the end. This is similar to competition between polymorphs. So we could think of this as having three morphologies. We've got left, right, and amorphous. But although predicting polymorphs is very difficult, I'd argue that left and right is much more subtle. With polymorphs, the different polymorphs typically have different growth rates and different stabilities, and it's those things which govern which ones you see. With chirality, because we've got this mirror symmetry, the left and the right are going to have the same growth rates, the same stabilities, and so it's much more subtle effects which are going to say whether you get a racemic mixture or whether you get one dominating the other. But we can still get, for the right parameter values, we can still get a system in which one will compete with the other and drive the other to extinction. So the model where we just had tetramers, hopefully we can use as a lesson to learn that very crude simplifications can lead to the wrong deductions. We had a model that looked like it got all the right elements in it, but it said you'd never get symmetry breaking, which clearly is not true. We do see symmetry breaking in them. But if we're more careful about our symmetry, about our reductions, and keep some more information about the size of the distribution, we can get models which hopefully will exhibit the correct phenomena. Okay, so thank you for your attention.
Do you have an intuition for how this would be affected by adding monomer addition and loss from the things? Because it seems to me that that what often happens, or what I often think of happening, at least maybe incorrectly, in a real crystallization, is that most of the events are adding a single or taking off a single unit. But when you have this abrasion from grinding, then you take off larger units. So this, I think, would be the abrasion that you're looking at here, taking off dimers in your case, but it could be decamers or whatever, but always the same size. Yeah. But if that's superimposed on a background of a large amount of monomers going on and off, maybe much more prevalent really in the total mass flow than the chipping. Do you have an intuition for how that would influence this?
I think this would still be very similar. So to get this size distribution, we had to solve the quadratic. If you this is the one that has monomers in it as well. And you see that these steps are all the same. So this is saying that C7 is the same.
So this is a histogram of the size,
This is
right?
size distribution.
Of the two
Yes.
hands.
Yeah, and this has got monomers in it.
Uh-huh.
This has got monomer addition and monomer removal in it. And these all look exactly the same. So I think these size distributions would look very similar. You can't do it exactly because to find the shape of this you have to solve a quartet, which you can't really do. It's not practical to actually solve it. But you'd still get very similar results. I think the same phenomenon.
From the outset, you would have thought that this model looks very similar to that of Yukio's, and still it behaves very differently.
Yeah.
Would you agree? Is that surprising or not?
I think because we've kept the dimer, the amorphous dimers in it. That's a really crucial difference.
I think this model has always the back reaction, even though the cluster becomes null. So he has no critical nucleus. I think, in the usual cases, the crystal size increases as the reaction back to or melting rate should decrease. So there is some preference to the forward direction, and that should be round up.
And that's what Vim does in his with this 1 over the cube root of the size, changes the size of the thing. Yeah. You bias the steps up and down according to the size of the particles you're considering.
I don't think actually it's not how you actually calculate that. The longer ones have a little small favor, I think it's
I thought that was quite similar to Sato's.
In my case, when the cluster size becomes bigger than the critical size, that means already a dimer. And then that means from tetramer and quatramer, they don't directly go back, they don't melt. But here you included all the back reaction. And then you end up the true equilibrium state, which is in a limited system. You will end up with a chiral. No, Rasenix did that. That might be the reason. Your transient, when does the equilibration take place? That might depend on the back reaction rate.
Maybe it depends on the back reaction, so actually it's much more than simulation of the grinding, so it was the activated, so it's a free parameter. It's the equilibrium formation, so maybe can be a difference. But I think maybe the major difference is maybe all these not of higher order. The difference is in your model you have this this axis that gives 3x2 that adds some very nonlinear. I think it's a major difference.
When you had up to size particles up to size 4, you didn't see symmetry breaking, which is the same as this, and then you went up to particles of size 6, and by going to size 6 you get more of a shape of the distribution, so it's a similar result. So that's because with size 6 you did get symmetry breaking.
So that might also be I don't know.
I see it.
Size 6? But you go to size arbitrary, 20.
I went to arbitrary,
And it doesn't work.
It does work.
It does work? What do you mean? It doesn't work.
So this is a crude simplification.
Yeah.
This is the one that doesn't work because you
I
only
see.
have
Yeah,
tetramers, you have
then
X1
it
micron.
works, fine.
And then we go to we go back to the full system, which has got anything, which is the total number. And this one does work.
But don't I understand that every particle size in yours has the same rate of growth and the same, so it doesn't have the feature that I think Saito's referring to, which is that there's a critical size. Above that, growth is dominant. Below that, dissolution is dominant or loss is dominant. Not for grinding.
This model had he didn't have fragmentation of size 4, but he did have fragmentation of size 6.
Well, maybe I shouldn't talk about his since I haven't looked at it as closely, but Waha definitely has two populations, one that's greater than the critical size and dominantly grows, the other one that's smaller than the critical size and dominantly dissolves. And the crucial feature in the simulation is that when you abrade a supercritical one, it becomes subcritical. So you can actually consider only growth of one class and only dissolution of the other class. So it is somewhat different.
Yeah.
So it's
This
interesting.
is very different. Isn't it?
Yeah.
And it is also difficult to understand, or it will be more rare to understand the simplification that from a determinate size cluster, they are not chiral. From the cluster size from 6 or 7, it is difficult to imagine that it is not chiral. The cluster should be grid for the crystals.
Yeah.
They are chiral.
Yeah.
So the approximation that they are not chiral, they are in the bottom. They are
Almost
chiral
anything
is in 2, 3, 4, but above 4 or 5, they are probably chiral.
Almost anything of any size is much more likely to be chiral than to be achiral. The question is, what's the duration of the chirality? And for anything that's not pretty big, the duration, in my guess, would be pretty short, so that it would behave as if it's achiral, even though almost all realizations of it at any instant would be chiral.
Yeah.
The model with the polymorphism says the energetics of the two phases should be different for the two polymorphs. Do you think, because since you're inserting energy, is there a possibility to try to stabilize the metastable form by grinding? Or it always will go to the stable form? Because it's inserting energy, right? Like to the system. And then if you start grinding, then you can take into consideration what about the energy.
So I guess it's
So I have an experiment, let's say, because if you take glycine, there's three polymorphs, but the two polymorphs, alpha and gamma, are very close to each other. But they have a completely different structure. And the problem is that if you have to move from one structure to another structure, you have to reorganize completely the structure of the cluster that you're forming. Now, upon heating, you can go from one to the other by inserting energy and going to something which is less stable at room temperature. But I feel that also by grinding you may be able to somehow to force the metastable form, if the difference is not very large, to force it to crystallize. And then you get some information about the organization of the clusters, how the cluster can in one form to reorganize to form the cluster in the other form.
It's possible.
But we're not taking into consideration energy here for the final steps. You see, the two states are identical and antimorphous. You cannot insert the stability of the final state.
Well, if you did it, it's possible because what you so you have you go from xk to x plus 1. You have these growth rate fragmentation. So the thermodynamic energy depends on the ratio A over B. So that's what governs your equilibrium stability. So you have one of these for if you've got reactions of type. So you've got two sorts. So you've got alpha and beta for crystals of type Y and A and B for crystals of type X. So you've got a thermodynamic stability which depends on which of these is biggest. But at early times, what's crucial is the growth rate. So what's crucial is really alpha. So you could have the system where this is bigger here. So at equilibrium you're going to see this type of cluster, but actually this has got the faster growth rate. It's just that the B and betas conspire to give you the opposite stability. So you could have this system where grinding might give you enough small materials actually mean that Y dominates X at short times, and that might exist for quite a long time in reality. The final conversion to the equilibrium system will take a long time.
There may be situations where even the keeper form, the form is less stable, but it may grow faster than the other form.
Yeah.
And then by kinetic control process, you may actually stabilize by grinding and growing the system.
Yeah.
Less stable.
In the polymorph context, the way that might work is that a less stable polymorph nucleates and begins to grow. And then, but if in the fullness of time a more stable polymorph nucleates and begin to grow, then you've lost because the more stable one will take over. But if you're grinding and can force those big ones that have been nucleated to become subcritical and dissolve, then you can keep them, because the majority one is autocatalytic, so that the other one is ultimately better. But if you keep it suppressed, then you can hope to keep it in a less stable polymorph, I should think. Yeah. There's a story at Yale when Lars Onsager, who was a sort of mysterious member of the department, he was obviously very, very smart, but he would not very often say anything. He would look and look and he'd smile and grin. He'd think of something funny and smile. Wouldn't say anything. Once he was the host for a visiting speaker, Sam Weissman, whom I referred to earlier. And Sam gave his talk and came to the end. There were a couple questions. Lars was sitting in the front row as the host. Like this. Quiet descended. Finally, the speaker, Sam, said, "Do I tell you to go home, or do you tell me to go home?" Are we at the end of the afternoon? I don't know.
Oh, you're the chairman of the discussion.
I am the chairman, yes, so I don't know what.
And of course, the discussion goes with the participants.
Yeah.
Not so much with the chairman. I was quite intrigued by August's talk, which really made connection, of course, with the ultimate question of the origin of life. And that was intriguing because it put in a much more definite sense the origin away from the hydrothermal events that many people have been thinking about, and also, of course, from the interstellar space, which a number of other people are thinking of, and put it straight to the beach, which again a few other people have been also thinking of for similar reasons. There was this paper by Bywater and this priest something in astrophysiology in 2006. There was this paper by Bywater and his collaborator, Origin of Life on the Beach, also in the context of peptides. You can print it out and look at that.
Bywater, abattu par Bywater sur l'origine de la vie et sur la plage. I don't see this paper. I don't understand what you mean.
So the origin of life needs to be placed somewhere, and you put it first of all to the Earth, away from other worlds, because you excluded panspermia. But other locations of the origin of life, of course, are hydrothermal vents, which is not compatible with your scenario, and yet others are interstellar space. There's many people who are thinking of making amino acids in interstellar space, which is a very different objective, of course. And some people think that has to do with the origin of life. So none of them is compatible with what you are saying. What you are saying is it should be at the surface, exposed to violent influences from the outside, which was one of the reasons why people thought the origin of life is better being served at the bottom of the ocean, because that's sheltered from still violent impacts. And radiation.
What's the question exactly?
I was saying I was intrigued by this new possibility of enhanced reasoning why the origin of life may actually be placed at neither of these two.
Try to translate. Because I don't understand.
Your location for the beginning of life is very different from some other models. Yes, some are hydrothermal vents, interstellar space, bottom of the ocean, otherwise maybe. So, what do you think of, maybe what do you think of the other models? Or, I don't know exactly what the question is.
What about the concentration of material? I think that one of the points that you really raised, Augusto, there was the problem of the concentration of the material. And the question is, how you concentrate materials. I think that if you take hydrophobic materials, they can be concentrated at the air-water interface. Because we have seen that at the air-water interface you are forming clusters, and you also incorporate the air-water interface on the one end, right?
And others can be incorporated by enhanced by evaporation, which is which can happen only on the surface.
So you need water in both cases. And what you need water in both cases, either for concentration of the water interface or by the evaporation, when you're creating some kind of crystallization or even amorphous material on the
And the nice thing about evaporation and air-water interface are that they happen at the same place.
Yeah.
So some things could be enhanced one way, some enhanced the other, but they'll be together.
Yeah. And if you find the phospholipid, for example, they're really very, very nicely, they self-assemble to form clusters of all kinds of air-water interface. And then you can assume also the formation of the cell, which is the vesicle, and then concentration within the vesicle, which can finally, and then you have reactivity within the vesicle, which can be regarded to the primitive cell, which can absorb energy in one case and then exchange material.
Of course, the beach could have been on Mars when Mars had water on it a long time ago. Maybe the conditions for the beach on sunny Mars were more favourable. People have theories whereby, well, it's known that impacts from the surface of Mars send bits of meteorites off into space and they hit Earth and they can carry seeds of life. And I've just got a notice today from astrobiology.
There's a magazine of astrobiology. Maybe that's what it means.
Saying there's a new paper showing that simple living systems could probably survive such a journey on a meteorite from Mars to
But then we still have, of course, probably either very much the same problem on Mars.
Oh yes, yeah. But I'm just complicating the issue.
But what did you have in mind when? I mean, you were thinking of cell interfaces being critical here to have the concentration.
People are saying that maybe the formation of a cell, of a vesicle, is actually a primitive cell.
Yes.
Now, people like Dimmer and others have found in meteorites also some kind of hydrophobic materials. And if you take these hydrophobic materials, which also contain other materials, and then you dissolve them, then you can form some kind of a primitive cell, where the other materials are included within this particular confined environment. Maybe then you can really start their activity. And Luigi actually has done these very nice experiments where he has demonstrated splitting of vesicles. Let's say you take some anhydrides with long chains, and if you hydrolyze them, then you can see that the vesicle can grow, and then it splits into two, and then they incorporate some kind of molecule like RNA or something like that, and they have seen Shostak and Luigi, and then you can some molecules within this compartment, and you can have splitting, and each cell contains some of the molecules which are inside the part. So this might be a kind of a confined part, and this can happen at their water interface, like what you suggested. So technically their water interface, and then this organization from a monolayer into a vesicle is quite feasible.
Yes, but in any case for the vesicles, you need a minimum concentration.
But I think
It's a
that
critical concentration to form the
but I don't difficulty of that, because as you say, if you take very small quantities of these amphiphilic materials, they can really suffer.
Yes, of course, but you need an CMC. It means, and today it was attractive this about the size, because it implies that you can be in the micromolar concentration, and you need to increase the concentration, and in process that can be repeated and selected, do you need it is tight. Tight is a good explanation, because when you have a lac or an ocean, and you must wait in geological time that they evaporate to get the concentration, and here this is a recycling, continuous recycling. That it means that it is necessary a moon. So, without moon it is not necessary. But it will be like in the future. The role of the moon.
I saw a talk
And there is no want in Mars.
in December by Barry Sharpless. He was in Stockholm, and he described chemical reactions. They're much faster on water, of much concentration. So they calculated with the markers, and they found that the water lies like a hydrogen surface, and the organic substrate, which is hydrophobic, with the help of the hydrogen bonding from water, will go much faster and accelerate rates of the reaction. And obviously, in this case, it would be similar. When you concentrate, the water acts like a hydrogen bonding network, and then you accelerate the reactions that are ongoing while you're concentrating.
There is another point on the beach. On the beach, the amount of carboxyl anhydride which was formed each day was very small and very spread away. And probably some very small crystal of N-carboxyl carboxyl amino acid were formed at a tiny concentration. And when the tide come back with peptides, previous peptide, the addition of one amino acid, the elongation of peptide comes or go step by step. One amino acid, and then the second one came later, maybe 10 years later.
But then what about hydrolysis?
Yeah, but the hydrolysis takes, the half-time of hydrolysis takes of the peptide takes about 100 years.
Yeah, but it is an acidic condition, because if you want to keep the anhydride, N-carboxyl anhydride stable, it must be acidic condition.
No, but N-carboxyl anhydride is stable in acidic condition during hours. Before, when on a beach N-carboxyl anhydride is formed, his stability can be maintained during hours. so he can wait for the next tide. And when the next tide comes, probably or maybe in an old peptide, the old peptide can be elongated for one amino acid and it's maybe only one. And the new peptide which is formed can be stable during months or years before to be hydrolyzed, partly hydrolyzed. And so by that way you can obtain slowly long peptide step by step, amino acid by amino acid. And then this is difficult to reproduce in a laboratory. Is what we can imagine on the beach.
Also, it's a long time scales.
Yeah,
Yeah.
it's a long time scale. And if some amino acid, and this we do it in the laboratory. If you polymerize, for example, with an excess of N-carboxyanhydride, you obtain precipitate, peptide which precipitate, and such peptides are removed, and they go on the sediment, and probably slowly they are hydrolyzed and they recycle the amino acid. But the peptide which is soluble stay, alive. He stay ready to react with another N-carboxyanhydride the day after, or the week after, and so on and so on. And so I believe that progressively such peptide can be elongated, and the peptide can be elongated. Mm-hmm. Is what we can imagine in this scenario. Of course, very difficult to prove.
But there are still differences then. You're talking about cells. And you, what? Vesicles, yes. And you're thinking of the vesicles being at the surface of the water, or?
No,
or even
you're forming a monolayer, and then after that, let's say, either during the evaporation of the water, maybe this can self-assemble it can be converted into a vesicle, and which can incorporate some material without this, and this compartment. One of the questions that Mike, the other Mike,
I would like to add additional information. In my slide, last slide, when I say that peptide can stabilize ATP, we have synthesized polylysine. Of course, polylysine is not a common peptide. It's polycationic peptide. And these polylysine we have attached covalently to polypropylene felt. I mean to say tissue
Felt.
of polypropylene.
Felt.
Oui. Of polypropylene. We have attached such polypeptide in a felt of polypropylene. And so with about 10 milligrams of such a felt, if you move such a felt in 1 liter of water solution containing a very small amount of ATP, 1 picogram of ATP, you move this felt in this water, and after 2 minutes, all the ATP is on the felt.
So, no, this.
So, it's an ATP extraction, very efficient ATP extraction. So, we can believe that big peptides, polycationic force, which is not the general peptide, we can believe that such a peptide aggregates, but still soluble, can collect NTP, which was synthesized in a beach at a very tiny concentration. And so, if the concentration is increased in this polypeptide, of course it's only spatial repeated polypeptide. So, if this concentration is improved, maybe something can happen, because these molecules are ready to react, because they contain a lot of energy. But this we don't do it. We just are able to collect ATP in water, and it's all green.
There's also another point, I think, that the protection of the organic material, because you're speaking very long time, right? You're speaking about long time. The peptide can react with another amino acid, with another amino acid.
Yes.
And then the question is the protection against, let's say, against radiation. So that this must happen in some way in the pores, in the beach or something like that, not on the surface itself, but maybe within the pores. And maybe this diffusion in the pores may somehow also concentrate.
That I don't know, maybe. But
because otherwise,
remember that
in such long periods, under very drastic conditions, you can really cleave peptides and you can really destroy them. We have to protect them. And then some people suggest that you must have this in the pores protected against.
Yeah, but you remember that in such a scenario, peptides are built each day, and so it's a balance between how fast these peptides are built and how fast they are destroyed.
You forget that you can discount again that you have already lipids in the solution. It depends on the time that you obtain under the other. It could be that it's not effective when you don't have the other, but it begins. It could be at first the artificial compounds to form the compartmentation and then to use the reaction here. It is not necessary much more coincidence in time.
You want to protect even if you said in university,
but you have already the micelles in the.
That could be.
Are there any other questions?
Just a remark. If you assume the absorption of these compounds on false rock or something like this, I think you have also a purification effect, because polar compounds, they are absorbed in those which might interfere with polymerization, so they are washed away. I think it's also a practice model to just assume absorption on some polar surfaces.
I want to ask maybe an unfair question, but a lot has been discussed in this conference about grinding. The question is there some relevance to this experiment of grinding on the origin of chirality and origin of life in a certain way? Because I was asking Mike the other night the same question, and he told me sand, of course, can be a very good grinder for material, and you present a model on the beach. Right? I think the French is much better if you say on flash.
The waves are also good for making micelles, yeah?
Yeah. The question is whether this experiment of Denmark and now Wien, the question is, because so much effort has been discussed in this conference, whether there is some kind of relevance to this experiment of the grinding.
Can I add an additional information that I find? When 10 years ago we imagine the primary pump. We were working with Degussa, a German company. And I say to Degussa, it's possible from this amino acid to form N-carboxyl hydride, but we have to protect amino acid with carbamoyl amino acid. And then, and I show you this reaction this morning. But in this reaction, when we write all the theory of the reaction, we obtain peptide, and then we have to say amino acid, if amino acid gives carbamoyl amino acid by reaction with isocyanic acid, of course the isocyanic acid is in water. And so, if the peptide is formed, isocyanic acid is still in water, and he reacts with peptide, with amino group of peptide, and the peptide must be carbohydrated. And so, no elongation is possible, except if this carbamoyl peptide must be deprotected. And so, I write the cycle for our Degussa company, and I say this protected peptide, when he come back on the beach, is deprotected in the same condition as this one makes N-carboxyl hydride. And this carbamoyl peptide must be deprotected by this gas mixture. And I make a report to Degussa, and Degussa say, we want to protect this reaction. We want to take a patent with this from this reaction. This one plus NO2 give peptide and H2. But I say to Degussa that this reaction is only on a paper. We never do it.
No matter.
Yeah,
and so
no barrier.
They say, you have to do it because we want to protect it if it works. And so we do it, and it was working very well. At the first time it was working. After 1 month of experiment, everything was done. So, and Degussa has protected this reaction. And so I was beginning to say, maybe something interesting in this cycle of reaction.
Who cares about
because
the origin of life?
you can imagine some new reaction, and it works, and they work.
I thank to hear for the first time that in addition to the patent, it could be something interesting in the reaction.
Yeah.
No, on the contrary, in our presentation in synthetic chemistry.
That's funny.
Thank you very much.
And now, I show you the concentration of ATP. It was about the same. And so if
if it's true this concentration with general peptide, because we do it only, I repeat, with polylysine. If it's true, it's maybe interesting. But a lot of work must be done in this field. A lot, because to test all the peptide is of course impossible. So,
I don't remember very well. Yes, your question. I believe it depends on the model that you have. In my opinion, grinding is a time machine. Then grinding only have a property, provoke dissolution growth process. And the key question is the dissolution growth process. There is another mechanism that do dissolution growth process. Then would be very interesting the grinding in the origin of homovitality if only is a time machine, because there is other process that can do the same. But if the grinding is the cause of the symmetry breaking, then it is not very interesting, because in nature there is not grinding. But in my opinion, grinding is only a time machine, and I believe that other mechanisms that generate dissolution growth are able to provoke chiral symmetry breaking. In this philosophy, I am working in equilibrium. I am working in temperature fluctuation. In the same, there is many mechanisms. And I think that it is interesting the grinding because it's a time machine, only that, not the real cause of symmetry breaking, in my opinion.
Can I come back to this question with the cells one more? I mean, I think there's still no compatibility now between the two of you. Or do you see that the two viewpoints are compatible or the same?
About the grinding?
No, about, you, on the one hand you were saying one should concentrate the amino acids, and this one would do in micelles.
In micelles or something like,
oh, yes, something
like vesicle.
And then on the other hand, Auguste is saying we may not need that, and maybe then even its mechanism would not work. I'm not sure.
But it is no incompatibility between both things. And of course, both things.
What do you mean? It's not. I mean, the two are different from each other. They don't work.
First stage and second stage.
First stage, second
It is
stage.
It's in different stage of the important thing, the more curious thing is the protection of the phosphorylated model. That is the interesting thing, the interaction with the peptide, in my opinion. And it could be implied that before the RNA wall is a protein wall.
I think it will be important.
The interesting experimental result, I think, is this: the protection of the hydrolysis of the phosphorylated compound by the protein. And then you can incorporate this in micelles or something, but it implies that you need before the peptide.
Yes.
The controversial point. I think it is this one.
So, but this would then mean, so if you are thinking of the first stage being what Auguste mentioned.
Synthesis.
Yes. That would happen at very low concentrations, one would guess.
Not at the box.
What?
Yeah, you can concentrate. I think the vesicle can concentrate.
But that's in the second stage. Now, which is the stage when it actually works? That is, if you have...
I interpret that you need to synthesize the polypeptide.
And would you do that without a vesicle or with a vesicle?
You need to concentrate the reaction.
So you would need a vesicle?
I think that yes, I think that you need it, because if you like to have life, and people believe that life started within a cell, and then a vesicle can be regarded as a protocell, and then you need energy, and you need exchange material from the cell out and inside, and you have to have separation. Actually, you have to have a compartmentalization and separation from the environment. And I think that at a certain stage, I don't know where is that stage, you need these vesicles.
Would you agree with that or not?
No. Vesicle, I don't know what it is, a vesicle.
It means
I know, of course, but no, when we studied the polymerization of N-carboxyl anhydride, we synthesized 4 different N-carboxyl anhydride. Valine, glycine, aspartic acid, glutamic acid, and alanine, I believe. And so we prepare these 4 N-carboxyl anhydride, and then we had progressively such small amount of such a mixture in water at the pH, at control pH at 6. And then after 10 minutes, we collect the solution and we do Malitov. And then we observe a distribution of peptides with molecular weight at about 800, so about 5 or 6 polypeptide average. And then we add a second injection of these 4 N-carboxyl anhydride, and so during 7 or 8 times. And progressively we saw the molecular weight of these peptides increasing until about 300 Dalton, 300,000 Dalton, 3,000 Dalton.
And the solution was always clear?
No. Not really. Not really. After the 7 injection, the solution was becoming not really clear, a little bit cloudy. And so we centrifugated, we get the powder, we analyze by Malditov, and we show that for the essential, this powder was polyvaline. Essential, for the essential. And the other one, still clear. And we continue, and so the distribution in Malditov was the following. At the beginning, it was like that. You know, with, of course, Malditov distribution. And then we obtain this, and then this, and then this, and the cloudy system was there. Polyvaline for essential. And so here we were at about 3,000 Dalton. But it was a lot of peptide, of course. We tried to analyze this with HPLC, and in this area we obtained I think 7 or 8 peptide with 7 or 8 amino acids. But for essential, it was not valine. Well, valine disappeared almost practically. And here we obtain essentially glutamic acid, I think.
the more soluble, of course. And we tried to continue our injection of 4N-carboxyanhydride, but Malitov stopped here. It was impossible with Malitov to go further.
Because the problem is that we might be able to form some clusters here.
Because Malitov dissolved the small one, but not the big one.
No, we tried related reactions with our racemats because we want to get the longer one by adding additional material. The problem is if you're forming some kind of the clusters there, maybe, and also I think that Kisha, what is that in Hamburg, that was doing the polymerization of N-carboxyanhydride. He was in your group. He was in your working group from Hamburg. From Hamburg, the person. And he was claiming that maybe you're forming some kind of, you're blocking the NH2 within the cluster of polypeptide, and therefore you block the
Yeah, wait a minute. We believe this.
Okay.
And Barbier in Orléans and Braque say the same thing. And then my co-workers, Eddie Sweat, I talked about him, was discussing with another young student, and they say, look, the Malitov is not a good machine to analyze this. And so they decide, these young people, they decide to analyze such a solution with GPC. Not the GPC, sorry. SEC. Exclusion.
What is it the same? Is it the same?
Yeah, exclusion chromatography.
Yes, yes.
Chromatography of exclusion. So it's not destructive at all, such a technique. And with this technique, these young people observed that the length of peptide was improving. And after that, we decided to polymerize not these 4 amino acids, but only one, lysine. The N-carboxyanhydride of lysine. And with lysine, but lysine this one. N-carboxyanhydride of the lysine protected by TFA in an epsilon position. And then, after the first polymerization, we obtain a precipitate. This precipitate was filtered, and then by deprotection here, this first precipitate was eight lysine. Sorry. 8 lysine, average of course, with a polydispersity 1.2. So 8 lysine with a short polydispersity. And we repeat the same reaction, N-carboxyanhydride TFA protected, with this amorceur. How did you say amorceur?
Initiator.
Initiator, with this initiator. And so we obtain not 8 lysine, but 48 lysine. And then we deprotect and with precipitation. And polydispersity again 1.3. Because he's protected and he precipitated. And again,
this is dendrimer?
yes,
A dendrimer.
is a dendrigraft.
Okay.
It's not a true dendrimer, it's a dendrigrafted of lysine. And the third generation gave 123 lysine. Again, precipitation, only dispersity very short, about between 1.2 and 1.4. And then, with such initiator, after deprotection, of course, we precipitate, and then we deprotect it, it becomes soluble. And after, with this initiator, we obtain a fourth generation, 360 lysine. Again, 950 lysine. And so, these compounds, 1, 2, 3, 4, 5, this one, the molecular mass of this one is 170,000 Dalton, with a very short distribution, because they precipitated before the deprotection. This compound precipitated, and we can wash it. And the yield of each of these reactions is about between 50 and 70% with starting material, with carboxyl anhydride. And so now these different compounds, different generation of polylysine are prepared by 50 grams by batch. 50 grams, 50, 50, 50, 50. And we prepare 100 grams of this, and we get, after cleaning, washing, by 50 grams of this finished product. And so these products have a lot of property. And so now I'm working a lot with such a compound. And not yet. I don't continue to work with many different and carboxyl anhydride of amino acid, but only with one.
This is the polyel.
It's polyel. And we start from lysine, from eurolysine, which is a Japan society working in France. Dans les champs de betterave, how did you say? In the land of sugar, because this L-lysine is made by the transformation of sugar through biotechnology. So in France, eurolysine are producing thousand and thousand tons of lysine, L-lysine. And so they give us lysine. When I say, I would like lysine, how many tons? They are ready to send me a truck.
Excuse me, is all these amino acid lysine is of one enantiomer? Or
yes, one enantiomer. This lysine is made by transformation through a battery or something like that. Biotechnology, yes.
Process and it's used for feed, for animal feed.
Exactly.
If you start with a combination, racemic combinations of these D and L.
Oh, we don't do that, because it's hard to find lysine, D-lysine.
Sorry. They say how many milligrams.
We don't like to compete with us. He works on the L, we work on the L.
Yeah.
We have an agreement, right? You don't work on the L, we work on L. You work on L, we don't work on L. We work on L.
You want to be not heavy.
Yeah.
So, of course, this kind of compound were protected. And now, it's not a joke. Since now 2 weeks, we have created a small startup to to produce such a compound and to try to develop some jobs around some application from this compound. So you can see that prebiotic chemistry go to some startup.
So, but this was in response to Mia, and you said you disagreed with Mia.
Well, the question is, Professor Eschen wants to say the following. Origin of life is an historical question. What we can do in origin of life is doing an artificial origin of life. And then the mix between the real origin of life and that and the artificial will not. And therefore I think that what we are learning in these course programs, that there might be many, many processes, there are many different scenarios, and everyone might have his own scenario. Like Mike the other day said, let us vote, who believes what. And I think in this course programs you have very frequently you have actually such kind of votes. Who believes on what.
Yeah.
And this is quite legitimate that we disagree.
It's quite what?
Legitimate that we disagree. I think this is quite clear.
So that's quite something. I am actually one thing I cannot imagine still, and maybe you can help me with this. If you think of the ocean is really vast, and that cannot be the medium where you think you will dissolve your amino acids. I would be more prepared to accept this if you're talking about smaller units like pools. There you wouldn't really have necessarily the tides that you want to have.
You say.
So how exactly are you really thinking of the big ocean as such? Or are you thinking of smaller ponds, or what do you have? What do you? I mean, I accept the rest of the picture, but I just want to know: are you really thinking about the
ocean is very vast.
Yes.
Yes, of course.
And that's what you're thinking, yeah?
Yeah, well, you take
but our problem in the primary point is to change the pH.
Yeah.
If you want to adopt this synthesis of this N-carboxyl anhydride, if you want to adopt this reaction, this one, and if you want to synthesize peptide, you have to change the pH very fast. So the only way to do is to imagine the tide. And if you imagine that the tide is in ocean, but I don't know,
Yeah, but you take Wachtenhauser, and you see the lifestyle that will come, where you have a lot of pyrite, and nickel complexes or something like that, carbon dioxide, COS, sulfur, H2S,
I know.
all these problems.
I know this word, but when you read such papers, Wachtenhauser proves nothing.
You know that he's a patent attorney, he's not a chemist, he does not have a position.
He's unable to synthesize peptide except by 2 or 3 peptide. I mean, dipeptide or 3 peptide, and with few amount of milligrams. And so I can believe that with such a yield of peptide, I mean at the end of the ocean or in sulfur crystal. So I respect the work of everybody, of course, but this kind of reaction, I can't believe that from this kind of reaction many peptides can have been produced and evolved.
I think we also should realize that when life emerged, the moon was very much closer to the Earth. And I think tides were much more violent than nowadays. So we have a lot of mixture in such a tidal model.
That's interesting.
Yes.
Yeah,
It's good or bad?
it's a good movement. Of course, everything was mixed. But
So,
you know,
We should continue to
we stopped our work in this direction, as I told you, because maybe we're wrong to have stopped here. Because if you have people to continue in this way, it will be possible to obtain larger peptides.
But you know that Peter Starvetsky from Lyon is doing this type of work.
Yeah,
I know that he has a paper now that he said yesterday.
very good.
Published.
But when we continue and when we obtain such a compound, polylysine, with about 1,000 of monomer, or here is about I don't know 300 or 400. These compounds have are almost spheric. This one is not, but this one began to be spheric, and how to say, the diameter of this one is about.
Do you think that they are relevant for the origin of life?
Hmm?
You think that these compounds are relevant to the origin of life?
No. But look, a little bit. But this is 4 nanometer. This one is 6 nanometer, and this one is about 12 nanometer. And you remember the work of Jean-Louis Raymond from Switzerland. He do from N-carboxynhydride dendritic graph of different amino acids. And he obtained not dendrimer of dendritic graph like that. He obtained a compound which was it's a polypeptide with such a dimension, and non-coded peptide, of course. And when we study such compound, you observe that these compound from this one, or this one, make aggregate. And so imagine the polypeptides coming from here, from different N-carboxynhydride. Imagine they become big like that. Of course they will form aggregate.
So this is what Luigi and Peter Frejevsky are trying to do.
Right.
But what they are doing actually, they are introducing histidine, glutamic acid, and I think serine and glycine, because they are trying to mimic one of the active sites of some of the chymotrypsin or some of the enzymes. But this is not just for that. But this is possible. But
my conclusion should be, or will be, in such aggregate, a lot of compounds can be concentrated. Would have been concentrated.
Yeah, this was done in dendrimers. Actually, dendrimers have been also used in order to concentrate materials inside them.
Of course. And so, if there is a place in water, they still soluble, but they make aggregate. And in such aggregate, a lot of small molecules can be concentrated and then maybe react. I don't know.
Could we imagine that in such type of polycationic, and you change the pH, you can be polycationic, and could be fixed by non-covalent solid phase synthesis an acidic amino acid, and then the reaction go to the row of the chain with other amino acids fixed on the, well, fixed or non-covalent fixed on the polymer. So we think in reactions beginning in amino acid residues, bonded electrostatic to the electrostatic to the polymer.
They still reactive.
Yeah, this is what you mean. You are testing, probably.
The ATP is still reactive.
It's still reactive. You can try to these polymers to be used to promote reactions by concentration. This is what you are doing.
The ATP is still reactive when it is concentrated in this polylysine. It reacts with an enzyme which is called luciferase, which makes a photon. So this compound, the ATP, not covalently bonded, absorbed on the polylysine, is still reactive with luciferase.
To be used as non-covalent solid phase synthesis.
Yes.
And this is what you are presenting, this one.
Yes,
of course. Yes.
Mm-hmm.
Very good. Very nice. Yes, yes, yes.
Yeah, it was very exciting and very insightful. I'm very impressed, and we all need to think more
But I
about this.
imagine that such a work, maybe not this one, since Merck says that it's not interesting on the original one. But maybe this one will continue in system chemistry.
Never know.
Good, thank you.
And
I think Axel tells us to go home.
Maybe with Axel
It was actually me who told me, right?
Yeah, I have to check my emails. But then
It was me who told me that he should not go any further than that.
No, so we have to check our emails.
So Meir needs to check his emails. I mean, you know that there's this story by Monique Rosing, who is saying that the continents are made through the weathering of the basalt, and that the weathering is accomplished through photosynthetic life. And he is really thinking of a vast scale on which this should happen, and it should all happen, of course, before 3.8 billion years ago, because that's the time when the continents were finally in place. They're still growing, of course, but that was the time when the continents were no longer, were already swimming on the heavier mantle. Basalt is, granite is lighter than the rest of the mantle. So by 3.8 billion years ago, they were all in place. So by producing such a huge amount of granite through the action of life, we should certainly not think of small ponds. We should rather think of on big scales, as you are doing, if I understand this correctly. So maybe you are really on the right track here. And thinking about small ponds will never get us there.
Many scenarios.
That is for the astrophysics. You need not only a planet as the care, you need also a planet with a satellite as the moon.
To another. And
you need the satellite.
So it's a
So this periodic change of the
Absolutely, yeah, that's quite right, yeah, indeed. And I'll print out the Bywater paper then.